Alright, recording has started. And here's the practice quiz, problem number 1. So let me give another minute. Okay, so on problem number 1, the format for this is this one right here is not in the ideal format. All the rest of them are. We want x to a power, and then we can use the power rule on each of these. So instead of starting out like this, I'm going to start out like this. I'm just going to rewrite the right-hand side. Now there's really an unwritten 2 over here, and an unwritten 1 right there. And that 2 goes underneath that. 1. Alright, now, I intentionally made a mistake when I rewrote this. Does anybody see the mistake that I made? Nobody seeing it?
Is it the negative 3e to the x?
That's correct. So it's not that. Let me give you a hint. It's not on the right-hand side of the equation.
Oh, the y prime?
That's correct. It's a common student error to put a prime when all you're doing is rewriting the original problem. So what we want instead when we do that is we just write the y. And then you put y prime next. Now, because of things like this, where you rewrite the problem often before you do it, the general rule is you always put something in for the left-hand side. For instance, another common student mistake, not only putting a y prime instead of a y, is then they leave the left-hand side blank, and then they take the derivative. 14x minus, and so on. And they keep going. Now, if you leave the left-hand side blank, that implies that it's exactly the same thing as what was in the step before it. But now it's not. It now represents y prime, not y. So, generally speaking, we always fill in the left-hand side. Don't leave it blank to save like a little writing. Put the y prime in there. And it's not y prime here, and it is y prime here. And then just keep always doing it. And then this is going to be plus 18x to the negative 4. And this is plus 2x to the negative 1/2. And then the derivative of e to the x is just e to the x. And the constant just stays out front. Derivative of a constant times a function is a constant times the derivative of the function. The derivative of minus 8 is 0, so we don't have to write anything there. So this would be dy dx or y prime. Either means the derivative. And give me some quick feedback on this. Let's go.
So just to be clear, so when you have the equation in the format y equals something, then you could write using the Leibniz notation the derivative of y with respect to x. But if you have like f of, I don't know, like in the homework there were like f of w's, would that just be d over dw?
All right, if it was f of w, the derivative could be df dw. It could also be still f prime. Notice the prime doesn't show with respect to what letter it is. You could put dw of f of w. I mean, there's different possibilities, all representing the derivative down here. These three are alternate notations. Good question. Just getting used to how the derivative has so many different ways it can be written. All right, let me look at the feedback on this one. If you could all just give me a little bit of feedback some way or the other. All right, I like that specific feedback about what you need to remember. All right, so number 2, quickly sketch y equals sine of x. From memory, make a quick sketch of that. Let me give you a minute. Okay, so this function is going to look like this, the sine. Now, notice I go up 1 and down 1. And then pi is about 3.14, so it's about 3 times the height here. 3 times that is over here. Now, the quarter points. sine starts here, the quarter point it goes to its highest, it keeps changing kind of by one height every quarter point, and then we connect this. With as smooth a curve as we can. And my curve is very childlike with my walk-on tablet. Let me try it a little one more time. It's a little better. All right. Now, the next question, and it keeps doing this, keeps repeating the numbers over again. On the same grid containing y equals sine of x, graph y prime. Just like we did the y primes before, we did them yesterday. I gave you like a third degree polynomial, and then I said draw y prime on the same graph. Do the same here. Okay, does anybody still need more time on this? All right, and before I do this, I'll just stay here. All right, so I find where it has horizontal tangent lines, right up here, so that becomes an x-intercept. Horizontal tangent line right here becomes an x-intercept. Now, between these two x-intercepts, the slopes are going to be either all positive or all negative. If you bought stock in this company, you'd be sad, you'd be losing money. And so the slopes are all negative. Where is it going down the most? It's going horizontal-ish over here, but it's going steepest right here. And its steepness down here is about maybe -1. So this, and then it comes back less steep over here. Then to the left of this, what are all these slopes? They are positive. You'd be happy if you own stock in this company. You're gaining money. But you're gaining money most right here, and then it's getting less and less the further you move to the right. And what's the slope right here? About 1. That would be about a 45-degree angle. About 1. And it gets smaller and smaller. Here. And then from here on, the slopes are positive in this portion. They get most positive, like if you own stock in there, you'd be a little bit excited. It's going barely uphill, but it's getting better and better, going steeper and steeper uphill. And finally, it's a steepness of about 1 over here. So it's gradually getting larger. And when we have that red curve shape, does that look familiar? What shape is that?
The cosine
That's
function.
the cosine. It appears cosine x. So we'll just kind of keep that in mind. When you take the derivative of the sine function, it looks like you got a cosine function. And a little feedback here. I know graphing with derivatives was something that was challenging for a number of people. So give me a little feedback. All right, let's come down. F of x equals 3x squared. Find the derivative by the definition of the derivative. So you got to remember the definition of the derivative and then work it out from there. It's the long way. And then B, which it said A again, by the power rule. And you should get the same answer both ways, but you know, the power rule way will be way faster. But and this is the kind of thing that's good for linking us up these together in our heads. Is that these are two alternate ways that get the same result. A new definition of the derivative. This is the one we'll stick with from now on. Just this one. Okay, does anybody need more time? All right, I'm going to go to the second part because the power rule is super easy. It's just 6x. And so that tells me, I better get 6x when I do the top way. F of anything is 3 times that thing squared. And f of x is 3x squared. Now this is really 3 times x squared plus 2hx plus h squared if you FOILed that out. And so then this is equal to the limit as h approaches 0. And if we distribute that 3 out, okay, and these two cancel each other out. What's left over is these other two terms that both have an h in them. Now the h's cancel. As h goes to 0, it drives this term to 0, and we get 6x, which agrees with my power rule. And we got that. Tell me, slight feedback. I'd like a little more review on something like this, or totally got this, don't need any more review, totally good with 2 ways to get the same thing on this. Alright, maybe we could still incorporate a little review with it. That's a good idea. Alright. Next. Now this part is a little more involved, and so I'm going to have you work with your groups on this one. X is the year, and Y is your company's profit in millions of dollars. So let's go. All right. So then we have Y prime at the year 2016 is equal to 23. Explain what this means. You're at a meeting of all employees of the company and you're on center stage. You need to give a nice quick description that isn't too technical, because you'll have people in the crowd who don't know what certain math words mean or anything. As simple as possible. So in your groups, come out with your best explanation of what this means. I'll pick on a group and a member in a minute. And remember, I gave instructions last time. If you feel real sure about an answer, just kind of delay a little bit. Let other people kind of go first, and then comment on maybe what somebody else is doing in your groups. Go ahead. And group leaders, make sure that the spokesman is aware that they are the spokesman for today. Okay, does anybody still need more time? All right, before I call in a group, let me put out a possibility. Is that the correct answer? And let me ask group 6 on this. Is this the correct answer?
I'm sorry, I'm just not sure.
You can always pass if you're not sure.
Yeah, we're passing the.
Okay, no problem. Um, let me open it up to anybody. Does this look like a reasonable answer for y prime of 2016 is 23?
That seems reasonable to me. That's more or less what we came to in our.
That's what you came to in your group. Okay. Anybody else?
I don't think it is 23 because y prime is talking to us about rates of change. So in 2016, this isn't the output, the exact output. This is the amount it's changing.
Ah, that is correct. My initial response, if I was a student in this class, I would probably put exactly what I wrote in red. But what this is y of 2016 is 23. If it didn't have the prime, this would be the interpretation. But since it has a prime in it, it doesn't mean this anymore. It means something else. All right, so let me go to group 3. Any idea of what the something else that it could mean is?
So does that mean that the 23 is the beginning profit that you've already earned, and then you earn another 23 million by the end of 2006?
You're going to something different. It's got to be something different than this. And you're saying maybe it's the beginning 23 million. That's in the right direction. But we want to include something that has to do with either the word slope or rate of change. Because that's
So,
what derivative is about. Yes.
so the $23 million is the difference between x value of a and a plus h. So that means that as you're going towards 2016, your instantaneous slope is at $23 million.
Very good. All right. Now this is technical language. We're going to have to put this in layman's terms because this is a meeting of all the employees of the company and most of them aren't going to understand this. But in technical language, in 2016, the instantaneous slope is 23. Now, to put this in language that everybody can understand, slope is, remember when I talked about the interpretation of slope? Does anybody remember?
As sensitivity of y
Sensitivity of y to what?
to x
To how much of an increase by x?
by 23.
It's the sensitivity
With the unit of one.
To a 1 unit increase. In x. Another definition of slope was the change in the output each time the input increases, not by an incredible small amount or anything like this, but by 1. Now that's the idea of slope. Okay, and we're going to have to get back into that to give an interpretation of what this 23 means in 2016. And so in easy language, from 2016 to 2017, the company's profits will do what? Anybody?
Increased by 23 million.
Yes. That's what we can say that the layman that's at the meeting will understand. Now, what we know is this is also the case, provided we stay on the tangent line. So, what's happening is here's 2016. And the company's profits, maybe they'd been a rocky ride. But right at 2016, the slope was 23. Meaning that if we went 1 more unit to the right, we would go up 23. The rise over the run is 23 over 1. 23 to 2017. Okay. Now, the actual situation is probably, it's not going to stay exactly on the tangent line. Maybe this trend of going up will continue to grow up and it'll go up even more. Maybe it'll reverse and come down. But provided the latest trend keeps going on, the company's profits will increase by 23 million, provided we stay in the tangent line. Now this gets into the meaning of 2 key concepts, slope and then instantaneous slope, which is the derivative. So just the slope itself is saying from 2016 to 2017 we'd increase by 23 million, but we know that this is just an instantaneous slope, so things could change. All right, so now that you've practiced on that one, let's go to this next one. X, years since 2010. Y is the price per share of stock in the retail company Target. And y prime of 6 is equal to 14. Explain what this means. So go ahead into your groups and everybody try and attempt on your own of putting in words. Everybody type it in and then just kind of talk it in amongst your group about which kind of language you prefer the most. Okay, 30 seconds more. All right, group 4, what do you got?
We went. Oh, this is Sally, by the way.
Okay.
We wanted to say that 6 years after 2010, the slope increases to 14.
Okay, that's kind of technical language. 6 years after 2010,
10. Sorry, I might have said 14.
the slope is 14. Okay, now the math people in the crowd might be able to understand this. Let's put it in easy language so that most everybody can understand this. Sally, you can answer this, or anybody can chip in here. Easier language.
In 2016, Target's cost per share was increasing at a rate of $14 per year.
Target's price per share was increasing at a rate of $14 per year. And I'm going to do one more. From 2016 to 2017, because this is often what the derivative is used for, which is to predict the future. When people are wondering, should I buy stock in Target? What they'll often do is say, well, let's look what's happened in the last year. Has the price gone up or has the price gone down? And let's just ride the current trend. Stocks have a tendency to kind of keep doing what they've been doing. They also turn around lots of times, but there's a little bit more tendency to keep doing what they've been doing lately. There's some momentum built up. From 2016 to 2017, I expect Target to increase in price by $14. Target stock. Provided it stays on the tangent line. So things change drastically sometimes, and it might not stay in the tangent line. Probably won't for a very long time, but that's usually our best guess to project out into the future. So the derivative, rates of change, how things are changing, how we might predict the future. Suppose this was 2016 and we didn't know what was going to happen in the next year. All right, any questions with those two problems? If no questions, now these last two though, notice I'm shifting your focus onto the interpretation. We got to keep going back and forth. We get the how to compute the derivative, but then what does it mean? And we got to be able to rotate back and forth constantly, and I'll be trying to exercise those muscles for you in these practice quizzes. And all right, questions on homework?
Could you go over number 59, please?
All right. Uh, 59. Okay, so find the equation of the line tangent to the curve, the given curve at A. All right, so now I'm going to do, I can find the derivative. I can do it the long way using the definition of the derivative. But now I have this super fast shortcut. I can also find the derivative by the power rule. 2 times negative 3 is negative 6x. The derivative of a constant is 0. So y prime is negative 6x. So y prime evaluated at 1 is negative 6 times 1, so it's negative 6. So this means that the slope m equals negative 6 at the point 1, comma, now how do I find the y coordinate? That's this point in space. I have to go back to this. If I put in a is 1, then 1 squared times negative 3 is negative 3 plus 2 is negative 1. So here is my slope, here is my point. I need to get the equation of the tangent line. Which is a point slope form. Y minus negative 1 is negative 6, x minus 1. And this becomes y plus 1, negative 6x plus 6, or y is equal to negative 6x, subtract 1 from both sides, plus 5. So that's my answer for A. And then use the graphing utility to graph the curve and the tangent line on the same axes. So I'll go to Wolfram alpha and I'll graph this and I'll graph this both together. Negative 3x squared, what was it? Plus 1 or minus 2?
Plus 2.
Plus 2. Plus 2. And then the other one was y equals, what was that?
Negative 6x plus 5.
it just nicks the curve. It's the tangent line at 1 comma negative whatever that point was. And it looks perfect, just nicking the curve. Does that answer your question, Kelly?
Yeah, I think I just did a computational error. I couldn't figure out how they got the y-intercept to be 5.
Okay. Let me point out something that usually throws a few people off on the next test that's going to come up. I'll throw in questions like, find the derivative of a function at a point, but use the original definition of the derivative. And then, maybe following that, I might ask a question very much like this. And what often happens is a significant portion of the class finds this derivative not by the power rule, the shortest possible way, but by the thing that I last asked them to do. If I had last asked them to find it by the definition, they'll just get stuck in that rut, and then they'll find this derivative by using the definition, and it'll take a lot more time than they have to get that definition, get that derivative, and so on. So you only have to use the original definition if I specify it. All the other times you can just use the power rule, the fastest way possible. Okay, any other questions? All right, if there's no more questions, homework, then let's go, we'll start into the product and quotient rules, 3.4.
Sorry, sir.
Yes.
Be able to do number 33.
Okay, and who is this?
This is Gerardo.
Gerardo, number 33, right?
Yes.
All right. So the directions are just find the derivative. So I'm going to do f prime of x. 4 times the 10 is 40 x cubed minus, and then this is an exponent of 1. 1 times 30 negative 32 is negative 32 x, dial down the exponent by 1, x to the 0, so any x to the 0 is 1, so it's just minus 32. And then plus e squared. Now, e squared, significantly, does not have an x with it. Because it doesn't have an x with it, it's just a constant. So its derivative is 0, just like if it was plus 10. The derivative of that 10 would be 0. But if you really want to look into it carefully, you could also think of it as times x to the 0 power. Because anything to the 0 is 1. So 0 times e squared is 0. 0 times x to the negative 1 would still be 0. So we'd get just plus 0. And so then this would be my answer. Gerardo, does that answer your question?
Yes.
Okay. Anything else?
So then when you have e to a variable,
Yes. That's
then
very
it
different.
means e to the variable minus 1.
If I had f of x is e to the x. Is that the case?
I would say yes.
It feels like it. because that's the way that the power rule works. But actually, power rule only works for power functions, x to a power. This is not a power function. This is a different type of function altogether called an exponential function. Exponential functions don't work this way. But this is the most common mistake made with this, so I'm glad you're bringing this up so we can get this resolved. The derivative of an exponential function e to the x is just exactly itself. And it's very, very different than the power rule. You don't change the exponent, you don't dial it down by 1 or anything like this. Exponential functions are crazy ones like this. They just have a very different rule. And we haven't gone into much as to why this rule is like this. But derivative exponential functions, so far we can only do exponential functions with a base of e. And then if it's just e to the x, we get e to the x. The other thing I pointed out last time is if you had something like f of x equals e to the 3x, f prime of x would still give you e to the 3x, but it would also give you an extra 3. That constant comes up in front. And at this point we're just kind of memorizing. That's how exponential functions, that's how their derivatives work. And it's good that we're reviewing that. That'll show up in this next section that we're going to be doing. Does that clarify it a bit for you, Kylie?
Yes, thank you.
You're welcome. All right. If there's no more questions, we'll go on. Interrupt me if there is, though.
Just so I've just for the exponential functions in this case. So you're basically, it looks like you're just taking the derivative of the variable portion and putting it in front of the e to the whatever term.
We'll get into that later of what's happening there. Yeah. For right now, whatever the constant is in front of the x, that'll show up again, right in front of the e to the 3x. And you are right, it is the derivative of that thing up there, but we'll get into that later on in detail. All right, so let's go to the product and quotient rules. We'll just get started here before we take a break. And for this, let me set up my whiteboard. So hang on a minute. All right. So if I have two functions that are added together, and then I take the derivative, well, that's easy. That's the sum of the derivatives. And we did that when we were doing things like f of x is 3x squared plus 2x. F prime of x, you're just taking this one separate and this one separate, 6x plus 2. And that you're really using this rule to do this. All right. So if that's the case, now we'll call this number 1. If that's the case, we would expect this to be true as well. The derivative of two functions multiplied together should equal f prime G prime. But the answer is no. This is not true. And it's easy to see that this is not true at all. Let's look at an example. Suppose f of x was 2x minus 9, and g of x is 7x plus 3. Now, if you do f times g, you have to FOIL this out. But what degree polynomial will you get? You'll get a second degree polynomial. There'll be x squareds in it. And then when you take f times g and its derivative, you get a first degree polynomial. So we know that the answer to this should be a first degree. When you take the derivative of any polynomial, you get 1 degree less than what you had before. But if you took f prime of x, you get 2. It decreases the degree by 1. G prime of x, you're going to get 7. You would decrease each of these degree by 1, and then f of prime of x times g prime of x there are no x's. You just get 14. But we are supposed to get a first degree polynomial. Alright, so the first thing we have to realize is that the derivative of a product isn't going to be anywhere as easy as the derivative of a sum or a difference. Derivative of a sum or difference, we just distribute that in there. But if it's things that are multiplied, or in this case we're also going to have divided today, like f divided by g, its derivative is not going to be f prime divided by g prime. It's going to be much more complicated. And by the time we're done, we're going to look back at the limit rules, and we'll say, God, I like the limit rules. All of them were like super obvious and exactly what would make it the very easiest thing that it could possibly be. But it turns out for derivatives, it's not that way. The derivative of a product and the derivative of a quotient are complex formulas, and we'll look not only as to what these formulas are, but why they are so complicated. Okay. Let me take a quick snapshot of this. Oh, that didn't work right. Let me get this. Now, let's come back and suppose we have a function like this, number 2. J of x is equal to x cubed e to the x. Now j is some function like f or g or h. Okay. Now, j prime of x. If I want the derivative of this, how do I get the derivative of two functions? Now, I know how to take the derivative of x cubed. That's 3x squared. I know how to take the derivative of e to the x. The derivative of e to the x is e to the x. Now this is the instinctive response that I would have to this problem. I would just take its derivative like this. But if we do this, we are making the same mistake that we just talked about. It's not the derivative of the first times the derivative of the second. It can't be. We're going to need to figure out, how do you take the derivative of a product, and especially when we know how to take the derivative of that, we know how to take the derivative of that, but we don't know how to take the derivative when they're multiplied together. We need a rule. It's called the product rule. We're going to look at this function like this. We're going to see that first one as f of x. We're going to see that second function is g of x. F of x like the x cubed, g of x like the e to the x. And now we're going to need a rule for the derivative of this in terms of f and g. And we know it's not going to be f prime of x times g prime of x. It's going to be some other manipulation of these two. And that's what we're going to look into after we take the break. So we'll start again. At 12:47 p.m. All right, we're going to continue again. All right, so J prime is not the first times the derivative of the first times the derivative of the second. But what it is, this is the derivative formula. It's the first times the derivative of the second plus the second times the derivative of the first. So if we look at this formula, is that this function is a combination of these two functions multiplied together, and this is the first and this is the second. Then the general formula is first times the derivative of the second plus the second times the derivative of the first. And that's how we wind up memorizing this formula. First times the derivative of the second plus second times the derivative of the first. You say it a few times and you wind up memorizing it. Alright, now if I was a student in this class though and I was asked to memorize this, I'd be like completely lost. I would say, yeah, there's the formula, but why in the hell is it that formula? That's a crazy formula. And I need some kind of justification as to why it's this crazy thing like this. And so that's what we'll go into next. Why it is. You know, I won't give you a total explanation, but I'll give you some big clues as to why we get something really goofy like this. And to explain why, we're going to start with, let me take a snapshot. And here. So number 3. Let's look at graphically. How we do 10 times 20. Well, we make a picture. A rectangle, 10 by 20. And we're trying to find the area of this. And if you divided this up into 10 little line segments, this into 20 little line segments, and then you made all the boxes, you'd get 200 of these little tiny, square centimeters, whatever they are. All right. Now, if we change the problem, so we made the 10 grow a little bit by 1. And we made the 20 grow a little bit by 1. So remember, rate of change is the change in the output every time the input increases by 1. Now, remember we were looking at J of x is f of x times g of x. See, when the input increases by 1, the x might increase by 1, but that could cause some change over here and some change over here. And then how does that change the total G over here? All right, so let's look at what's happening over here, visually speaking. If 10 increased by 1, we would get, let me try to make this about the same, 10, 20. Now, we added one little extra portion. We added one little extra portion over here. So, the original is like this, but then we have this extra part that's added over here. All right, this part in red is, I'm going to say, the change in the output. Output function. When the input increases, it could cause two things to change. And how does that change the total area of the whole thing? All right, now, the change in the output now, it's not the total output. I'm not looking at just the total area. I'm looking at just the red portion, the change in the output. Well, there's different components to it. I'd say, well, there's this component right over here. And that is, now this is 1 and this is 1. So this could be 1 times 10. And then this one is a rectangle 1 high by 20 wide. And that's this one right here. And then you have this one more rectangle right over here. That's a 1 by 1 rectangle. Now, we say the bulk, most of the change in the output. Is coming from right here. How much one of them changed times the previous value of the other. And then how much the other thing changed multiplied by the other thing. It's kind of like looking over here and seeing this distributive property is going to be happening. If you had to FOIL this out, you'd still have the 10 times the 20, which would give you this area. But you'd also have this. You'd also have this. And those are those two portions over here. And then the one part, the 1 times the 1, we're going to say, that's going to be kind of inconsequential. It'll be really, really small compared to the others. The most of the change is going to be happening from those things. And so let's take our situation now and let's call, we'll go to number 4. Let's let f of x be a very specific function, 5x. And let g of x be 2x. The derivative dx of f times g is how much f times g changes when x increases by 1. Now, that's, I'm going to put provided we stay on the tangent line. That's the kind of basic representation of what the instantaneous slope means. And that's what a derivative is, an instantaneous slope. It's how much the output changes every time the input increases by 1. But since it's an instantaneous slope, we kind of think provided we stay on the tangent line. All right. Now we're going to use this notation delta x. Delta x means change in x. You might be used to that from slope. Delta y over delta x. Or delta, yeah, delta y. Right. If delta x is equal to 1, how much is the change in the f going to be? Well, every time x increases by 1, f of x blows that change up by 5 times as much. And the change in g is going to get doubled, so it'll be 2. Okay. So let's draw a picture of this, but before I do that, let me take a quick picture. This in here. So now I'm going to have the picture for this up high, and I'm going to draw a rectangle where I'm going to put the 2x vertical and the 5x horizontal. I don't know what x is, but that's just kind of for some arbitrary value of x. Now, let me draw it again. X, 5x for some value of x. But now we have, if x increased by 1, this one increases by 2. And this one increases by 5. And then I draw this up here. Okay, now, what's going to be the area of this part right here? This is going to be a rectangle whose width is 5x, whose height is 2, so it's going to be 5x times 2. What's going to be the width of this, the change in the output? It's going to be height of 2x times a width of 5. And then this part, 2 and 5, is going to multiply together to be 10 up here. All right. Now, the change in the output. How much did the output change going from this rectangle to the bigger rectangle? Is 5x times 2 plus 2x times 5. Now, this is going to be the vast majority of the change. The 10, we're going to wind up leaving out. And why we're going to wind up leaving it out is beyond the scope of this course. It's kind of beyond my understanding as well. The more I've kind of looked into that, the more I get confused. But it's this is the vast majority of the change. This winds up being inconsequential. And because we're going more towards the instantaneous slope, and we take smaller and smaller intervals, this winds up disintegrating down to basically nothing. And so the let's say the bulk of the change, in the output is this. And now this is f of x. What was the 2? Well, look at, if you took f prime of x, you'd get 5. If you took g prime of x, you'd get 2. So that 2 was really g prime of x. And this was g prime of x, or g of x, and this was f prime of x. And the change in the output is that's the output. How much that's changing is its derivative. And so we can kind of start to see a little bit why this rule is this strange way. Because if you are changing two different inputs simultaneously, the f function and the g function, when x increases by 1, how that's going to affect the whole result depends on the current value of f and the current value of g, and if they're going to interplay like this. And let me do a print screen with this. Oops, I got my arm. And put this in. And all right, let's pause here. Questions and comments at this point.
So, like according to your notation for number 4, like the first one that says like derivative with respect to x of the product of f and g. So you could, with something simple like this, you could just take the product, like which would be 10x squared, and then find that that derivative is 20x, but also use the product rule to get 20x. But will that be applicable with more complicated polynomial expressions, or no?
You said something about the square of the f of x?
Right, so if you have, because you're saying it's the product of f and g, so that would be 5x times 2x.
Okay.
That's x squared, and you're getting a 20x. And you're getting the same thing by using the product rule, by splitting it up into multiplying f of x times g prime of x plus g of x times f prime of x. You also get 20x doing it that way. So, but I guess my question is, with simple expressions, is it interchangeable, or as we get more advanced, do we want to abandon trying to simplify what's within the parentheses?
Yeah, I'm not 100% sure I understand what you're saying, but what I think you're saying is you're looking for a bigger pattern and saying, does it always work this way? And let me just note that this particular problem was really simple with two linear functions. And so any kind of generalizations you make from this might not at all be true in general, because I had to pick two really simple functions to make this idea kind of clear in here. So yeah, I would hesitate to make a generalization for a shortcut that you're seeing in here. We'll look at some more complex ones, and then you can try out your theory on the more complex. And I think then you'll be able to kind of answer that question for yourself. All right. Any other comments? I have a quick feedback question that will help me for how fast I go and in future classes as well. If you could just get on the chat line and answer these questions individually for me. How many of you are, or are you taking notes as if you were in class and writing out all the notes, or are you just kind of relying on the OneNotes to take your notes for you? And does it make it easier that the OneNotes are there, so like, you know, if you get behind in your notes, you realize, oh, I can always go back and look and see what's in OneNotes and so on. And you know, what's the relationship of this with taking notes for you? Okay, that's kind of how I was imagining the way that most of you are doing it, because I tend to use taking notes as kind of a way to keep myself engaged too, to keep my mind from wandering. All right, let's now a little more feedback. What I just went over, was it too abstract? Or did it seem like it related to this problem, and are you getting comfortable with it? Or where were you with this latest explanation with the product rule? I know it's going to get a little more clear when I do some real examples, but just how did this theoretical explanation feel to you? Okay. All right, let's go. I know when I took calculus, something like the product rule was just, here it is, memorize it. And no explanation was given as to why it's so crazy is how it is. And I, for certain things, when I get kind of overwhelmed, I can just kind of say, all right, I'll just memorize this. But at a deeper level, it bothers me when I don't get more of an explanation. Let me come back in my notes where we were at. All right. So the last thing we did, I think it was number 4. So I think I'm on number 5 now. If I'm not, somebody can correct me. Let's do f of x is equal to 2x squared minus 3 times 7x cubed minus 5. We're going to find f prime of x. We're going to do it 2 different ways. A, using the product rule. Now, since we're going to be using the product rule, f prime of x. Let me write down the product rule, and if this was my homework, I'd be writing this out from memory every time I used it. And it would be first, well, that one I don't put in parentheses, first times the derivative of the second plus the second times the derivative of the first. And I write that out from memory every time I'm using it, and then soon I realized, oh, I really have this memorized really well. Okay? So f prime of x, I look up here, it's going to be the first times the derivative of the second. Now, if this was a complicated thing, I'd write d dx of the second thing. But since it's not complicated, I can just take its derivative. But let me just kind of show you how it would look if I wasn't just taking its derivative. First times the derivative of the second. Now, notice I'm not putting a prime there. Instead, I'm doing d dx. I get in the habit of taking the derivative this way. If I put the prime up here, let's say I step away from it and come back 20 minutes later, and look at it, and I'll think, oh, that was just to the first power or something. And so d dx is more clear for me, plus the second times the derivative of the first. Take the derivative like this. Now you don't have to write it out like this, where you're showing what you're taking the derivative of each time. You could have just put in the result from there. But the first time I do it, I like to just show the real process. And it's really handy to have this as a tool. You'll eventually get to some functions that are so complicated that you can't take that derivative very quickly in your head. And so you'll want to write out the derivative of what it is you're going to be taking. All right, so then this derivative is 21x squared. The derivative of minus 5 is just 0. This derivative is 4x. And the derivative of minus 3 just goes away because it's plus 0. So then f prime of x is 21x squared times 2x squared minus 3 plus 4x times 7x cubed minus 5. And notice I might be tempted on the left-hand side, since it's the same all the way down, to leave it off there, but I never leave it blank. Because it's when you leave it blank that you tend to make mistakes, like sometimes it's y, sometimes it's y prime, and if you left it off and left it blank when it had actually changed from y to y prime, it's wrong, and so on. So I always put it in on the left-hand side. And I distribute out 42x to the fourth, 63x squared plus 28x to the fourth minus 20x. And are there any like terms? Yeah, these two are like terms. That turns out to be 70x to the fourth and I got it. So that's how I would use the product rule. First times the derivative of the second plus second times the derivative of the first. Now let's do this problem again without using the product rule. Now, I'm going to FOIL these two things out. In fact, in case, if I was actually doing this derivative, I probably wouldn't do it with the product rule. I don't need the product rule. Remember the other problem where we had...
Professor?
Yes.
This is what I was asking. I guess I didn't express myself very well. So I guess this is what I was asking about, the ways to do it.
Mhm.
And so, like, just expanding this, these two expressions and then taking the derivative that way.
Yes. That should give exactly the same answer because it's a legitimate alternate way to do it. That is correct. So that's what we're going to do right now, is we're going to FOIL these two things out and then take its derivative. And we don't need the product rule to do this one. I probably wouldn't use the product rule to do this one. I bet you this is longer using the product rule. When we need the product rule is when we have something like f of x equals e to the x times x squared. Then there's no way to take that derivative without a product rule. All right. So now this time though, if I FOIL this out, now let's just FOIL it out way up here. This is going to be 14x to the fifth minus, and then when you distribute to the 5, it's 10x squared. And then when you distribute to 3, it's minus 21x cubed. Distribute, the last one is plus 15. All right, so f of x was also 14x to the fifth minus 10x squared minus 21x cubed plus 15. So f prime of x, if I do this, 15 times 4 is 50 and 20 is 70, x to the fourth. And notice that's matching exactly what was up here. Then let's jump to the next highest power term. 3 times 21 is minus 63x squared. That's exactly matching this one. Let's take the derivative of this next one. 2 times this is minus 20x, and the derivative of 15 is 0. This is exactly the same as what we got when we used the product rule. And this is why when I first introduce a new concept, I usually pick a problem that can be done in more than one way so that we can verify that the product rule really works. It gives us the same answer we would have gotten had we not used the product rule. Any questions? All right, let me take a snapshot of this. Okay, and let's do another problem. I think that was 5, so then this is 6, and f of x, well, let's just say y. Y equals e to the x times the cube root of x. And find dy dx. Alright. So before I did this, I would rewrite this problem. There's an unwritten 1 here. This number comes underneath here. So this is the same as x to the 1/3. Okay. So now that I have it in a format that is easy to take the derivative of, I will go into dy dx, the derivative. And now I'm just going to think of the product rule as I write things down. It's the first times the derivative. Remember when you do d dx but don't put a y there, that's that's a verb. It's an action. Take the derivative with respect to x. First times the derivative of the second plus the second times the derivative of the first. And then figure out what each of these is. This derivative is 1/3 x to the negative 2/3. This derivative is just e to the x. So dy dx is, now we put all these three together. I'm going to put the coefficient up front, the simplest function, which is kind of a more polynomial type function, negative 2/3. And then the most complicated in the back, which is exponential, plus e to the x. Okay, that would be my answer. Any questions? All right, a quick note. Sometimes you won't see your answer looking like this if you look in the back of the book and check your answer. You might see things like this. Also correct. Just to get you used to it. There are two terms here. What's common between these two terms? Well, they both have an e to the x. Number-wise is a 1/3 here and nothing here, so I wouldn't factor anything yet, any of the coefficients. But what about x to a power? Now, this causes some people some confusion. If it was x to the second plus x to the fifth, people know, oh, I can factor out, you take the smaller of the two exponents. You can still do that with these two. You can say x to the negative 2/3 is the smaller of those two exponents. Then, what's left over from this term? 1/3, because everything else has been factored out, plus, and then, now the e to the x has been factored out here. What must be the coefficient on this x so that when you add this to this, you get x to the 1/3? Well, because we'd add the coefficients if we multiplied these two together. This must be x to the first, because 1 minus 2/3 is 1/3. So it could look like this. You might see the answer like this in a textbook instead of like this for a final answer. But it means the same thing, and I'll accept either one. You know, it's factored out form or written like this. Doesn't really matter to me. All right, let's do another quick one, and then we have to go to the quotient rule. All right, let's print screen. Oh, I think I got my arm. No, I got this thing. Okay, and then stick it in here. All right, let's, number 7. Y equals 7x to the 4th. I'm going to do it y prime the way I've always done it so far, which is 4 times 7 is 28x cubed. B, I'm going to do it with the product rule. Now, I don't recommend it. But if you do that with the product rule when you don't need to, the only time you need to do it with the product rule is when there's two different functions of x. This first number is just a constant, so you don't need the product rule. But if I did it with the product rule, it would be first times the derivative of the second plus the second times the derivative of the first. But this one is 4x cubed. And the derivative of 7, derivative of any constant, is 0. So this one turns out to be 28x cubed plus 0, but notice it's the same answer. So if you use the product rule when you didn't have to, because it was just a constant times a function, it's not that it's wrong. It's just you're doing more work than you have to, but it's still a legitimate answer. And paste that in. Let's go to the quotient rule. Now, the quotient rule, I'm not going to be able to give you an explanation of why it is the way it is for a while, because we've got to get to some more complicated, like more advanced stuff before the quotient rule will make sense. So what we're going to do now is I'm just going to tell you what the quotient rule is. You're going to memorize it and use it. And then in about a week or so, I'll be able to give you an explanation of why the quotient rule is the way it is. All right, so the quotient rule. Since f minus g prime is equal to f prime minus g prime, we might expect f divided by g prime to be f prime divided by g prime. But the answer is no. This is not true. Similar way that the product rule was necessary, same thing, the quotient rule will be necessary. The quotient rule turns out to be this: f divided by g prime. To do the quotient rule, I always think of an arrow going up. And it helps to remind me to start with the bottom function. G times f prime minus f times g prime over g squared. And it's crazy. It has a little bit of similarities to the product rule. Kind of looks like the product rule on the top. One times the derivative of the other, and back and forth. But it has a minus sign instead of a plus sign. And it starts with g instead of starting with f. And then it also has this divided by g squared at the bottom. It's crazy. Now, we actually I don't memorize it like this. I think of it more like this. There's a top function and a bottom function. And we start from the bottom. So it goes bottom times the derivative of the top minus the top times the derivative of the bottom bottom squared. The bottom doesn't get the derivative. Maybe I should take the parentheses off. There's no derivative on the bottom. You just square it. And so we won't get into why this works until a fair amount later. Let's just show how to use it and that it works. So example 1. If I have f of x is equal to x cubed over e to the x. Then f prime of x is equal to, and again, you're going to have to memorize this. But the way I memorize it is bottom times the root of the top minus top times the root of the bottom over the bottom squared, instead of trying to memorize all these kind of things. So then I do it. Let's do it. I put an arrow here to remind me to start at the bottom, times the derivative of the top, minus the top, times the derivative of the bottom, over the bottom squared. And this derivative is 3x squared. This derivative stays at e to the x. So I'm going to get 3x squared e to the x for the first term, minus x cubed e to the x for the second term. And then e to the x squared, power to a power, what do I do with those? Is it e to the x plus 2? Or is it e to the 2x? Which one is it? It's power to a power multiply. And if I ever get confused about something like that, I just kind of do a simple example in my head. That's x times x cubed, and that's x times x. And there's really 6 x's, so I multiply those two. And I remind myself of the principle, and I put it down like this. Now, is it okay to leave this as the final answer? Answer is no.
Can't you simplify it?
Yes. How do I simplify?
Take e to the x.
Very good. In the numerator, there's e to the x. There's also something more common, but that's the part that's going to cancel. So it's all a part I really need to factor out. Because I could factor out x squared as well. Now, you can think of e to the x squared as e to the x times e to the, or e to the 2x as e to the x times e to the x, if you want, because you'd add the exponents. And one of these is going to cancel with one of these. And then that one, there's my final form for the derivative. So I'm really very adaptable. I don't mind how you get the final form of your answer, except when there's a simplification that needs to happen and you got to reduce. Then you need to reduce. I will take points off if you would have given me this answer. when you could have easily reduced out the x's, e to the x there. Okay. Any questions on this with the quotient rule? All right, so now let me first of all put this here. Write down the product rule and the quotient rule from memory. So just test your memory. See if you can write them both out without looking at either one. Okay, and then verbally, the product rule, instead of f prime times g, it's first times the derivative of the second, plus second times the derivative of the first. Excuse me. Now the quotient rule.
Bless you.
Thank you. The quotient rule is, instead of g times f prime and so on, it's bottom times the derivative of the top minus top times the derivative of the bottom over the bottom squared. All right, and let's look at one other one. I think we're on number 10. Is that right? Y equals 4 over p cubed. Find dy dp a using the quotient rule. Alright, so everybody go ahead and do this one. I'll give you just a minute and then I'm going to put up the answer. Dy dp by using the quotient rule. Okay, let me have you stop. Didn't get all the way, that's fine. Say dy dp is bottom times the derivative of the top minus the top times the derivative of the bottom. Now, you could have just written what the derivative of 4 was, which is 0, and derivative of p cubed, which is 3p squared. But I'm just writing out all the steps. So, the derivative of any constant is 0. This is 3p squared. So then I'm going to get this whole term zeroes out, so all I get is minus 12p squared over p to the 6th, or dy dp is negative 12p to the negative 4th power. That is what this simplifies down to.
Would you get the same answer if you did 4 times p to the negative 3rd?
That is very good. That's anticipating what my part B was going to be. Great
Sorry.
job. So now we're going to do this without the quotient rule. And we can do this thing without the quotient rule because four over p cubed is the same as 4p to the negative 3 power. So then y prime is minus 12 p to the minus 4. And is that the same answer? It's exactly the same thing. And once again, we're realizing you only need to use the quotient rule or the product rule if the variable appears twice. If one of them's a constant, you don't need the quotient rule or the product rule. And in this case, we didn't need the quotient rule. But if you did use the quotient rule, it wouldn't be wrong. It's just that you're going to be doing more steps than you would have needed to. All right, the homework. Is this section 3.4, which I'll be spot checking tomorrow. And questions or comments?
I do have one question.
Yes.
When can we use it without the quotient rule? We know.
Repeat that again. I got a lot of disturbance.
What I was asking is, I just wanted to know, how do we know we can use it without the quotient rule?
How do you know when you can use it without the quotient rule? All right, because there was no variable up in the numerator. If that had a 4e to the p power, then you'd have had to use the quotient rule because the variable is up in the top and the variable is down in the bottom. But when there's no variable in one of those two places, then you don't really need either the quotient rule or the product rule. Does that clarify it?
Yes.
Okay. Is that Dominic? Or who is that I was talking to? Or is that Gerardo?
Yes.
Gerardo. Okay. All right. Anything else? All right. We'll stop here. I'm going to turn off the video. And I'll see you all tomorrow. You're welcome.